Let us briefly discuss transformations of bases and vectors. Transformation of bases and vector is a fundamental concept in linear algebra and play a crucial role in structural mechanics. We will first discuss transformation of bases, then move on to transformation of vectors, and then an advanced version of transformation, which is called transformation of maps. We have already mentioned that basis is very important to define any vector within a vector space. Basis is a set of linearly independent vectors that can span a vector space. So imagine if we have this vector space and it is shown by two independent bases. There is a this green vector. That green vector can be decomposed into two distinct components with respect to the bases. Thus, a basis can be thought of as a building block of a vector space. So these two components, they can build up the whole vector. Please remember that a vector space can have infinite bases. There are only three bases which we can imagine. Beyond three bases is difficult to imagine. Now, this green vector is defined in the black basis, which is EI or E1, E2. This black basis is an orthogonal basis because both the basis vectors are making 90-degree angle with each other. We want to express the same vector in the different basis, which is EI star basis. Then the basis transformation matrix will actually help us to represent this green vector in the EI star basis. In order to be more clear, let us define this green basis in our EI star basis. We will call EI star basis as the new basis and EI basis as the old basis. When we say EI star, we mean E1 star, E2 star basis. And when we say EI basis, that is our orthogonal basis, which is E1, E2. Just for understanding, we are trying to deal with a 2D space. So in order to define the new basis in the old basis, we can write E1 star as 2E1 plus 1E2. So E1 star is made up of two copies of E1 and one copy of E2. So this dimension of E1 star basis is now defined in old basis. Let us do the same thing with E2 star, which is minus half of E1 plus quarter of E2. So we have defined our new basis in terms of old basis. Obviously, in order to find out the vector position in the new basis, we have to first of all determine how is the new basis arranged within the old basis. Collecting these terms, which are the coefficients of E1, E2, we get something which is called F or a forward transform matrix. So this is a 2 by 2 matrix having the 2 and 1 in the first row and minus half and quarter in the second row. This forward transform matrix actually transform old bases into new bases. If we want to do other way around, in other words, if we want to find out our old bases in terms of new bases, we can do the same thing. We can define our E1 in E1 star and E2 star basis. Similarly, E2 can be defined in E1 star and E2 star basis. So E1 is quarter of E1 star minus E2 star. E2 is half of E1 star plus 2E2 star. This is called a backward transform. It is called backward because it transforms our new bases into the old bases. Previously, we had the forward transform, which was transforming our old bases into the new bases. Once we have defined our bases. Now we are in a better position to find out our vector within the old and the new bases. Let us write the components of our green vector in the old bases, which is the black bases. So V is equal to 1 times E1 plus 1.5 times E2. So 1.5 is the vector in the EI basis. We can define the same V in our new basis, which is E1 star, E2 star basis. And that is 1 time E1 star plus 2 time E2 star. So in EI star basis, our vector V is having component 1 and 2. Please note that the vector V will have different components in different bases. However, its magnitude and direction will stay the same. That is invariant, as we have discussed previously. Now let us do a thought experiment. Let us see that whether we can extract the new components of our vector from the old components by using the concepts of forward and backward transforms. As we discussed over here, the forward transform actually converts the old bases into new bases. So if we use the same concept, we should say that if we multiply the forward transform with the component of the vector in the old basis, we should get the component in the new basis. So the forward transform is multiplied with the vector component in the old basis, and we find that we get a component 1.25 and 1.375. This is different from the actual component of the vector in the new basis. Whereas if we multiply the backward transform with the old components, we find the exact component of the vector in the new basis. So there is a clear question in mind. Why in the case of bases, the forward transform help us transforming the old bases into new bases, and the backward transform helps us in transforming the new bases into old bases. But in the case of vectors, when we multiply the forward transform with the vector representation in the old basis, we don't get the correct answer. We have to multiply the backward transform with the vector in the old basis to get the actual component of vector in the new basis. And the answer lies in a clear logical explanation of this. Let us see. Imagine we have a vector v which is having coordinate 1, 1 in some basis e1 star, e2 star. This e1 star, e2 star is an orthogonal basis. So this is different from what we have over here. Now, if we double the size of our bases, in other words, if we take another basis which is twice the size of the old basis, we see that the vector components are halved. So by increasing the size of the bases, we actually reduce the components. Please remember again that the vector direction and magnitude will stay the same. It's only the component which are becoming halved, so that apply the Pythagoras theorem on that, our magnitude comes out to be the same as this one. Similarly, if we rotate our basis e1 star, e2 star, we see that the vector actually rotate in the opposite direction. So if e1, e2 star is rotated clockwise, the vectors seem to be rotated counterclockwise and coming close to e2 star. So initially there was some distance between the vector and the e2 star. After rotating clockwise our axis, the vector has come closer to e2 star. So it goes in opposite manner, based on the logic that the vector components are reduced if we increase the basis size, and if we orient our bases, the vector moves in the opposite direction. Tells us that we have to multiply the opposite transformation as the basis transformation. Please remember, we said that the backward transform is inverse of the forward transform. So if we want to find out the component of a vector in the new basis, we have to multiply with the opposite or the inverse transform as that of the basis. In other words, we have to multiply the backward transform in order to get our vector in the new vector space. Another relevant concept related to the transformation is direction cosines. Direction cosines, or sometimes called directional cosines, are a set of trigonometric ratios that describe the orientation or direction of a vector in a three-dimensional space. They are used to represent the angles between a vector and coordinate axes or any other set of mutually orthogonal axes. So in the figure, we have a set of orthogonal axes, which is x, y, and z, small x, small y, and small z. And we have another inclined set of orthogonal axes, which is capital X, capital Y, capital Z. The directional cosines actually help us describing the orientation or directions of vector in these spaces, or they are used to represent the angles between the vector and the coordinate axes. In this figure, we have got this red vector whose magnitude is equal to 1, and it is making angle theta x with the small x-axis, theta y with small y, and theta z with the small z-axis. And the direction cosines are thus L is equal to cos theta x, M is equal to cos theta y, and N is equal to cos theta z. Since the direction cosines are cosines, therefore they lie in the range between -1 and +1. The sum of the square of direction cosine is equal to 1. So that is following a Pythagoras theorem. So we can take the component in all the three axes and square them, and that should be equal to 1. Similarly, the sum of the squares of the direction cosine property ensures that the direction cosines completely describe the direction of a vector. Now, instead of this vector, which is shown in red, we can also have another orthogonal space, which is capital X, capital Y, and capital Z. So the capital X will make its own direction cosines with the small x, small y, small z axes. The capital Y will make its own set of direction cosine, that is L2, M2, and N2 with respect to small x, small y, small z respectively. And similarly, the capital Z will make its own set of direction cosines, which is L3, M3, and N3 with the small x, y, z axes. So once we collect all these direction cosines, we can find out some other properties of direction cosines, such as the column elements, which is L1 square, L2 square, L3 square, that is also equal to 1. Similarly, multiplication of pair of direction cosine and addition gives us 0. All these properties are shown over here. So a direction cosine help us in the coordinate transformation. Direction cosines are used when transforming vectors or coordinates from one set of orthogonal axes to another set. It must be appreciated that we can use direction cosines when the axes are orthogonal. In structure mechanics, we are encountered with different set of coordinates, especially if we are considering a structure which is before application of the load and a structure after application of the load. So these two different coordinate axes or different vector spaces. A transformation between these two axes can be performed by using the concepts which we have developed, like the change of bases, the vector positions with respect to different bases, and also the direction cosines. Now, let us discuss another important concept which is called linear maps, and that is very extensively used in structural mechanics. Linear maps help us map one coordinate system to the other coordinate system. Linear maps are simply linear transformations or linear operators. Linear maps always act on vectors. They help in transforming one column vector into another. So imagine we have a linear map in a 2 by 2 system, that is 5, minus 1, 4, and 3. This is a particular linear map. This linear map, whenever is operated on a vector, it will transform that vector. So we have taken a unit vector in E1 direction and applied this linear map on this unit vector. The linear map has taken the unit vector into another vector which is having components 5, 3. In other words, linear map has transformed 1, 0 into 5, 3. Similarly, we can have linear map applied on E2 unit vector, and it can transform that into minus 1 and 4. We can have, instead of unit vectors E1, E2, any other form of vector having two components, and linear map will transform that, will take it from one position to another position. Normally, the unit vectors are used to find out the vectors from which the linear map has been developed or constructed. Like, for example, the by multiplying 1, 0 unit vector with the map 5, minus 1, 3, 4 gives us a vector which is 5, 3. So it is the linear map is considering 5, 3 vector, and there is another vector which is minus 1, 4. In other words, if linear map is made up of these two vectors. Let us discuss further the geometrical concepts related to linear map. A linear map, when applied on any vector, will keep the grid lines parallel, will keep the grid lines evenly spaced, and will keep the origin stationary. So imagine we have this system, and in this system we can see a red square. Every side of this square can be considered as a vector. Now, if we apply linear map on each and every vector, after transformation, imagine we get something like this. Instead of instead of square, we get a rectangle. So the two sides which are on the y-axis, they stay the same size. The horizontal sides, they are stretched. So we can say that the linear map has actually stretched this square into rectangle. But please see, the linear map has kept the grid lines shown parallel. Also, the grid lines are evenly spaced. It hasn't destroyed the distance between the grid lines, and the origin stay the same. Similarly, these vectors, they can be converted into a diamond shape after applying the linear map. So that means that a shear deformation has taken place. The grid lines satisfy these conditions. They are parallel, they are evenly spaced, and the origin is stationary. Some important properties of linear maps are that a linear map of the resultant of two vectors is equal to linear map operated on the vectors individually. So imagine we have this vector which is green one and another vector which is red one. If we apply a linear map individually on the green vector and then apply it on the red vector, whatever we get, wherever the linear map takes that vector to, or however the linear map transforms that vector, that will be the same as, first of all, adding the two vectors, getting the resultant purple vector, and then applying the linear map onto the purple vector. That has been discussed over here. The linear map onto a particular vector applied individually is equal to the linear map of the resultant of these two and then applied. The other property of linear map is the scalar multiplication. So we can have a particular vector within a space, multiply that with a scalar, and then operate the linear map onto it. And that will be equal to, first of all, applying the linear map operator onto the vector and then later multiplying the scalar multiplier. Because of these two properties of linear map, we use the term linear while defining the map. We can also have nonlinear maps, but in structure mechanics, most of the time, we deal with linear maps. The analogy of the analogy with structure mechanics would be that initially, before application of any load, a particular element might be in the position shown over here. After the application of the load, we might have either extension, orientation, or both extension and orientation. So if we know the linear map for the whole structure, we can easily multiply the vectors which are making up this element with the linear map, and we can straight away get the final position of this element after the application of the load. We can clearly appreciate that how powerful the linear map concept is. That is why linear map are very extensively used in defining stresses and strains within the structural system. Linear map transformations. Let us now discuss how a linear map can be defined in our new axis system. So as before, E1 and E2, or symbolically called as EI, is the old basis, and E1 star, E2 star, or defined as EI star, is the new basis. Imagine we have a linear map which is defined in the EI system. Imagine we want to find out the linear map of a vector which is in a new basis. So we have got a vector in a new basis, and we want to find out the linear map of that vector in the new basis. That vector, which is, as we discussed, in the new basis, has to be multiplied with the forward transform in order to get the equivalent vector components in the old basis. Please note, we are talking about the vector. So the vector has to be multiplied by a transformation which is opposite to the basis transformation. Once we find our vectors in the old basis, we multiply that with the linear transform which is corresponding to the old basis. So we get a transformed vector in the old basis. After that, we have to multiply this vector with the backward transform in order to get the corresponding vector in the new basis. We can also say that if we take the map corresponding to the old basis, multiply that with the forward and the backward transform, we will get the L star, which will give us the components straight away in the new basis. That comes out to be 9 by 8 and 7 by 2. We can appreciate from this discussion that linear map transform the input vectors. They don't transform the bases. And also, in order to find out our linear map transformation in the new basis, we have to multiply that with the backward and the forward transforms. So we have to multiply it with true transformations, unlike previously when we were transforming a vector. In case of vector, we would multiply just either a forward or a backward transform to get it into the transformed space. In the case of linear map, we have to multiply that with the forward and the backward twice. So thus two transformation has to be done in order to change our linear map from the old basis to the new basis.